Linear Algebra II, Lecture 12, Problem Session. Problem 1. Define a map phi from R3 times R3 to R as follows. The value of phi at the two vectors x1, x2, x3 and y1, y2, y3 is equal to x1, y1 plus 5x2, y2 plus a minus 3 divided by 4 times x3, y3 plus 2x1, y2 plus 2x2, y1 minus x1, y3 minus x3, y1 minus 5 divided by 2 x2, y3 minus 5 divided by 2 x3, y2. Determine for which values of the parameter a, which is a real number, this formula defines an inner product on R3. Solution. In order to check that phi is an inner product, we need to check that this map is symmetric, bilinear, and positive definite. So let us check all these three conditions one by one. Let us start by rewriting this formula in a different way. So we can write that the value of phi at the pair x1, x2, x3 and y1, y2, y3 of two vectors in R3 is equal to the product of the following matrices. First, the row matrix x1, x2, x3, then the 3 times 3 matrix of the coefficients in this long formula. So this is a matrix with the coefficients 1, 2, minus 1, 2, 5, minus 5 divided by 2, and then minus 1, minus 5 divided by 2, and a minus 3 divided by 4. And then the column matrix y1, y2, y3. So it is easy to check that if we multiply these three matrices together, we get exactly this long formula. So if we denote the column vectors x1, x2, x3 by bold x, the column vector y1, y2, y3 by bold y, and this matrix 1, 2, minus 1, 2, 5, minus 5 divided by 2, minus 1, minus 5 divided by 2, a minus 3 divided by 4, if we denote this matrix by a, then we can write that the value of phi at the pair bold x and bold y of two vectors in R3 is equal to x transposed times a times y. So this is just a different way to write this formula. Let us note that A is a symmetric matrix, so it is equal to its transpose. So now, if we want to compute phi evaluated at the pair bold y and then bold x of two vectors, then according to this formula, this is equal to y transposed times a times x. Note that this product is a 1 times 1 matrix, it's just a real number, which is the same as 1 times 1 matrix. And 1 times 1 matrix is equal to their transposes because a 1 times 1 matrix just consists of one diagonal element. So we can write that this is equal to its transpose. So now when we compute the transpose of this product, we should take the product of the transpose matrices in the opposite order. So we get x transpose times a transpose times y. But since we know that a is equal to a transpose, this is equal to x transpose times a times y, which is exactly phi evaluated at the pair bold x, bold y. Consequence, we have just proved that our map phi is symmetric. Now let us check that this map is bilinear. Since we already proved that it is symmetric, it is sufficient to prove that it is linear in one of the arguments. So let's take the left argument. So let's do the computation. Let's evaluate phi at the pair of vectors. The first vector is x plus z, and the second one is y. Using our previous formula, this is equal to x plus z transposed times a times y. The transposed of the sum of two matrices is equal to the sum of the transposes of these summands. And also matrix multiplication is distributive. So this is equal to x transposed times a times y plus z transposed times a times y. And the first summand here is exactly phi of xy, and the second summand is exactly phi of zy. So we have just proved that our function phi is additive in the left argument. Since it's symmetric, this means that it is bi-additive. Similarly, if we evaluate phi at the pair lambda x and y, then this is equal to lambda x transposed times ay. Lambda x transposed is equal to x transposed times lambda transposed, but lambda is a scalar, so lambda transposed is lambda, and scalars can be moved everywhere in matrix multiplication, so this is equal to lambda times x transposed ay, which is exactly lambda times phi of x, y. And this implies that phi is linear in the left argument and hence bilinear because it is symmetric. So the first two conditions are satisfied for all values of a. They don't depend on a. So now let us check the final condition and find out for which values of a our function phi is positive definite. For this, we need to evaluate phi at the same vector x1, x2, x3 as a left argument and x1, x2, x3 as the right argument. So if we write down the formula, we will get x1 squared plus 5x2 squared plus a minus 3 divided by 4 times x3 squared plus 4x1, x2 minus 2x1, x3 minus 5x2, x3. We need to try to write this expression as a sum of squares, maybe with some coefficients. We start with looking at the summands x1 squared, 4x1, x2, and minus 2x1, x3. So we can write this sum of these three summands as x1 plus 2x2, so here 2, it's 1/2 of this coefficient, plus 2x2 minus x3 minus 1 is 1/2 of this coefficient, and all this squared. So if we take the square, we will get all these three summands, and then we will have three extra summands. One of them is 4x2 squared, so we subtract it. Then x3 squared, we subtract it, and then minus 4x2 x3, so we subtract it as well. So now the sum of these two brackets equals exactly the sum of these three summands in this expression. And then we just write the rest, just copy it from the previous expression, plus 5x2 squared plus x3 squared with a coefficient a minus 3 divided by 4 and minus 5x2, x3. So by the way, there is a lower index 2 missing here in this summand. So now we can simplify this expression to x1 plus 2x2 minus x3 squared plus x2 squared, which is 5x2 squared minus 4x2 squared, plus x3 squared with a coefficient a minus 7 divided by 4, so a minus 3 divided by 4 is here, and minus 1 comes from here. And finally, minus x2, x3, so minus 5 comes from here, and plus 4 from here. So now we look at the summands x2 squared and minus x2, x3. So the first big square remains the same. And then for the second part, we take x2 minus 1/2 of this coefficient, so minus 1 over 2x3 squared. So if we take the square, we will get this summand and this summand. And then as an extra summand, we will get 1 divided by 4x3 squared. So we subtract it. And then we copy also plus x3 squared with a coefficient a minus 7 divided by 4. And now when we simplify this expression, we will get x1 plus 2x2 minus x3 squared plus x2 minus 1/2 x3 squared plus a minus 2 x3 squared. So now we have written the value of phi at x comma x as this expression, which is the sum of three squares with some coefficients. So here, this is a square with coefficient 1. This is always non-negative. This is a square of a real number with coefficient 1. This is always non-negative. This is a square of a real number with coefficient a minus 2. So for this expression to be always non-negative, we need a minus 2 to be a non-negative real number. Additionally, this expression attains the zero value only in the point 0, 0, 0, if and only if all coefficients at our squares are non-zero. In other words, a minus 2 is greater than 0. Therefore, the answer is that our function is an inner product if and only if a is greater than 2. Problem 2. The inner product on R3 is defined such that the vectors v1, which is 1, 1, 1, v2, which is 1, 1, 0, and v3, which is 0, 1, 1, form an orthonormal basis. Find a non-zero vector x in R3, which is orthogonal to the standard basis vectors e1 and e2. Solution. In order to solve this problem, we know that this new inner product on R3 is not a standard inner product. So the answer to this question is most probably not E3, which is orthogonal to E1 and E2 with respect to the standard inner product. But this inner product in this problem is different. So in order to find something which is orthogonal to some vectors, we need the coefficients of these vectors with respect to an orthonormal basis. So to solve this problem, we need to find the coefficients of E1 and E2 with respect to the orthonormal basis V1, V2, V3. In order to find these coefficients, we write our basis vectors as columns, then we take the vertical line, and then we write the coordinates of E1 and E2 in the standard basis. If we solve the corresponding non-homogeneous system of linear equations, we will get exactly the coordinates of E1 and E2 in the basis V1, V2, V3. So let's start with this matrix and try to reduce it to a row echelon form using Gauss elimination. So we start by using this 1 in position 1, 1 to eliminate everything else in the first column. So we subtract row 1 from row 2 and from row 3. Row 1 remains the same, row 2 becomes 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 1 is minus 1, 1 minus 0 is 1. And row 3 becomes 1 minus 1 is 0, 0 minus 1 is minus 1, 1 minus 0 is 1, 0 minus 1 is minus 1, 0 minus 0 is 0. So now we can swap row 3 and row 2 and multiply row 3, the present row 3, with minus 1 to get 1 in the position to 2. Row 1 remains the same, row 2 becomes row 3, and row 3 got placed in the place of row 2, and the sign is changed, so row 2 becomes 0, 1, minus 1, 1, 0. So now we use this one to kill this minus 1, so we add row 3 to row 2. Rows 1 and 3 remain the same, and row 2 becomes 0 plus 0 is 0, 0 plus 1 is 1, 1 plus minus 1 is 0, minus 1 plus 1 is 0, 1 plus 0 is 1. And finally, we subtract row 2 from row 1 to kill this 1. Rows 2 and 3 remain the same, and row 1 becomes 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 1 is minus 1. So these two columns now give us the coordinates of the vectors E1 and E2 in the basis V1, V2, V3. In other words, the vector E1 is V1 minus V3, because the coordinates are 1, 0, and minus 1. And the vector E2 is minus V1 plus V2 plus V3, because the coordinates are minus 1, 1, 1. So now we want to find a vector x in our space in the form x is equal to x1v1 plus x2v2 plus x3v3. And the conditions which we have, we want x to be orthogonal with respect to both e1 and e2. So if we have coordinates of vectors in an orthonormal basis, the inner product between these vectors is just the sum of the products of the corresponding coordinates. So we use this to rewrite now our conditions. So the vector x is orthogonal to e1 if and only if x1 times 1 plus x2 times 0 plus x3 times minus 1 is equal to 0. So in other words, x is orthogonal to e1 if and only if x1 minus x3 is equal to 0. Similarly, x is orthogonal to e2 if and only if x1 times minus 1 plus x2 times 1 plus x3 times 1 is 0. So the second condition is minus x1 plus x2 plus x3 is 0. So we have now written the condition for the vector x to be orthogonal to both e1 and e2, and we got a system of two linear equations. So let us now solve the system. So the matrix of the system is 1, 0, minus 1, minus 1, 1, 0. If we add row 1 to row 2, we get the matrix where row 1 is 1, 0, minus 1, and row 2 is 1 plus minus 1 is 0, 0 plus 1 is 1, minus 1 plus 1 is 0. So this is now the matrix of our homogeneous system of linear equations. The second equation reads x2 is equal to 0, and the first equation reads x1 minus x3 is equal to 0. A non-zero solution to this equation is x1 is equal to 1, x2 is equal to 0, and x3 is equal to 1. So the vector 1 times v1 plus 0 times v2 plus 1 times v3 will be orthogonal with respect to both e1 and e2 in our new inner product. So this gives that the answer, our vector x, which is orthogonal to both e1 and e2, is the vector v1 plus v3. And this is a vector 1 plus 0 is 1, 1 plus 1 is 2, and 1 plus 1 is 2. So the answer is that the vector 1, 2, 2 is orthogonal to both e1 and e2 in our inner product. In fact, any non-zero scalar multiple of this vector will also be an acceptable answer to this problem. Problem 3. Consider the Euclidean space of all polynomials of degree at most 2 with the inner product given by the following formula. The inner product between f and g is the integral from 0 to 1 f times g dx. Let n be the subspace of this Euclidean space, which consists of all polynomials which have value 0 at 0. Find an orthonormal basis in n. So this is a typical problem where one has to use Gram-Schmidt's orthogonalization method. So let us start by finding some basis in n. So a general polynomial of degree at most 2 can be written as a plus bx plus cx squared. And the condition that f of 0 is equal to 0 is equivalent to the condition that a is equal to 0. So an arbitrary element in n can be written as bx plus cx squared. Consequently, x and x squared form a basis in our vector space n. So let us apply Gram-Schmidt's process to the vectors x and x squared. So according to this process, the first vector, we should take the first vector, which is x, and divide by its length. So here is a computation. So the length of x is the square root of the scalar product between x and x. The scalar product between x and x is the integral from 0 to 1 of x squared dx. And this is simply the evaluation at x is equal to 1 of the primitive function x to the power 3 divided by 3. So this is equal to 1 divided by 3. So the length of the element x is 1 divided by the root of 3. So if we divide x by 1 divided by the root of 3, we will get root of 3x. So the first element in our orthonormal basis of n is the polynomial root of 3 times x. We denote it by g1 of x. Now about the second vector. So before we can determine the second vector, we determine an auxiliary vector g2 tilde, which is by definition the second element in our basis, which is x squared, minus the projection of x squared on the subspace spanned by g1. The formula for that projection is a scalar product between x squared and g1 times g1. But we know that g1 is x divided by the length of x, so we can rewrite it as x squared minus x with the coefficient, the fraction, where the numerator is the scalar product between x squared and x, and the denominator is the scalar product between x and x. And we have computed that the denominator is 1 divided by 3. So let's compute the numerator. The scalar product between x squared and x is the integral from 0 to 1 of x cubed dx. The primitive function is x to the power 4 divided by 4, and we need to evaluate it at x is equal to 1. And we get 1 divided by 4. So our auxiliary polynomial g2 tilde is x squared minus 3 divided by 4 times x. And the second basis vector is defined as g2 tilde divided by its length. So let's compute the length of g2 tilde, which in reality means let's compute the square of the length of g2 tilde, which is a scalar product between g2 tilde and itself. So this is the integral from 0 to 1 of x squared minus 3 divided by 4x squared dx. So when we open this, we will get x to the power 4 minus 3 divided by 2x to the power 3 plus 9 divided by 16x squared. And then the primitive function for this is x to the power 5 divided by 5 minus 3 divided by 2 times x to the power 4 divided by 4 plus 9 divided by 16 times x to the power 3 divided by 3. And we need to evaluate it at x is equal to 1. So the first summand will be 1 divided by 5, the second summand will be 3 divided by 8, and the third summand will be 3 divided by 16. The common denominator is 18, so from the first summand we have 16, from the second one minus 30, and from the last one 15. And when we compute this, we get 1 divided by 18. So the length of g2 tilde is 1 divided by the root of 18. And now we can say that the following two polynomials form an ONB in n. The first polynomial is root of 3 times x, and the second polynomial is root of 80 times x squared minus 3/4 x. This is answer to problem 3. Problem 4. Let M be the set of all vectors x in the Euclidean space E4, which satisfy the equation x1 minus x2 plus x3 plus x4 is equal to 0. Let V be the vector 1, 1, 1, 0. Determine an orthonormal basis in M, an orthonormal basis in M orthogonal complement, the projections of V onto M and onto the orthogonal complement, and the distance from V to both M and to the orthogonal complement of M. Solution. If we look at the definition of M, we see that an vector x belongs to M if and only if the scalar product between x and the vector 1 minus 1, 1, 1 is 0. This means exactly that the orthogonal complement to M is spanned by the vector 1 minus 1, 1, 1. Let's denote it by W. So if we use the Gram-Schmidt process to this one linearly independent vector, we get the vector W1, which is equal to W divided by its length. And this is a vector 1 minus 1, 1, 1. its length is the square root of 1 square plus minus 1 square plus 1 square plus 1 square. So this is a square root of 4, which is 2. And we get the vector 1 divided by 2 times 1 minus 1, 1, 1. This is an orthonormal basis in the orthogonal complement to M. Next, let us proceed by trying to find some basis in M to which we can apply then Gram-Schmidt process. So M is given as the set of solutions to the linear equation x1 minus x2 plus x3 plus x4. So the matrix of this equation is already in the reduced echelon form. So we can take x2, x3, x and 4 as free variables. And then we can rewrite the equation as x1 is equal to x2 minus x3 minus x4. And then the trivial equations for the free variables, x2 is equal to x2, x3 is equal to x3, x4 is equal to x4. And now we write the same thing in the vector form, x1, x2, x3, x4, the left-hand side, is equal to x2 times 1, 1, 0, 0, plus x3 times minus 1, 0, 1, 0, plus x4 times minus 1, 0, 0, 1. And the consequence of this, that the vectors u1, which is 1, 1, 0, 0, this one, u2, which is minus 1, 0, 1, 0, this one, and u3, which is minus 1, 0, 0, 1, this one, these three vectors form a basis in M. So let's do Gram-Schmidt. We start by normalizing the first vector. So a1 is equal to u1 divided by its length. u1 is 1, 1, 0, 0. Its length is 1 square plus 1 square plus 0 square plus 0 square, which is 2, and then we take the square root. So we get that a1 is equal to 1 divided by the square root of 2 of the vector 1, 1, 0, 0. In the next step, we look at the auxiliary vector a2 tilde. So this is u2 minus a1 with the coefficient, the scalar product between u2 and a1. Since a1 is u1 divided by the length of u1, we can rewrite it as u2 minus u1 with the coefficient, the inner product of u2 and u1, divided by the inner product of u1 and u1. So now we can do the computation. u2 is a vector minus 1, 0, 1, 0. u1 is a vector 1, 1, 0, 0. The scalar product of u1 and u1 we already computed, it's 2. And the scalar product between u2 and u1 is minus 1 plus 0 plus 0 plus 0, it's minus 1. So we get u2 plus 1 half of u1. And this is minus 1 plus 1 half is minus 1 half. So here 0 plus 1 half is 1 half. 1 plus 0 is 1. 0 plus 0 is 0. We can also delete this 2 here, and let's consider the vector a2 2 tilde, which is a vector minus 1, 1, 2, 0. This is twice a2 tilde in order to delete the denominator in our expression. And then we normalize this vector. The vector a2 is the vector a2 2 tildes divided by its length. So it's a vector minus 1, 1, 2, 0 times 1 divided by the square root of minus 1 squared plus 1 squared plus 2 squared plus 0 squared. So it's the square root of 6. The answer is that a2 is 1 divided by the root of 6 minus 1, 1, 2, 0. Great, now we need to do the third vector. a3 tilde is u3 minus a1 with the coefficient, the scalar product between u3 and a1, minus a2 with the coefficient, the scalar product between u3 and a2. And this we can rewrite as u3 minus u1 with the coefficient, the scalar product between u3 and u1 divided by the scalar product between u1 and u1, minus a2 2 tildes with the coefficient, the scalar product between u3 and a2 2 tildes divided by the scalar product of a2 2 tildes with itself. And so a3 tilde is equal to minus 1, 0, 0, 1, this is u3, minus u1 is 1, 1, 0, 0, the denominator is 2, we have computed it, and the scalar product of these two vectors is minus 1, 0, 0, 0, it's minus 1. And then a2 2 tildes is minus 1, 1, 2, 0. The square of its length is 6, we have computed it, so we have 6 in the denominator. And then the scalar product is 1, 0, 0, 0. it's 1. So we have this expression, and when we compute it, we will have minus 1 plus 1/2 plus 1 divided by 6. It's minus 1 divided by 3. And then 0 plus 1/2 minus 1 divided by 6, it's 1 divided by 3. 0 plus 0 minus 2 divided by 6, it's minus 1 divided by 3. 1, 0, 0, it's 1. So if you multiply this with 3, we will get the vector minus 1, 1, minus 1, 3, which we now normalize. So we divide it by its length. So A3 is A3 to tilde divided by the length of A3 to tilde. This should be this formula, which is equal to minus 1, 1, minus 1, 3, with the coefficient 1 divided by the square root of minus 1 squared plus 1 squared plus minus 1 squared plus 3 squared. And we get that this vector minus 1, 1, minus 1, 3, with the coefficient 1 divided by the square root of 12. So the answer, the vectors A1, which is 1 divided by the square root of 2, 1, 1, 0, 0, A2, which is 1 divided by the square root of 6, minus 1, 1, 2, 0, and A3, which is 1 divided by the square root of 12, minus 1, 1, minus 1, 3. These three vectors form an orthonormal basis in M. So now we have to compute projections and distances. Recall that all this we need for the vector 1, 1, 1, 0. The easiest thing is to compute projection on V on M orthogonal complement. So this projection is equal to W1 times the scalar product between V and W1, or in other words, it's W times the scalar product between V and W divided by the scalar product between W and itself. So the denominator here is 4, and the W is 1 minus 1, 1 minus 1. If we take the scalar product of these two vectors, we get 1 minus 1 plus 1 plus 0. So it's 1. So the projection of V onto M orthogonal complement is 1 divided by 4 times 1 minus 1, 1, 1. And the length of this vector is exactly the distance from V to M. So this length is 1 divided by 4 times the square root of 1 plus 1 plus 1 plus 1, so square root of 4, which is 2, and the answer is 1 divided by 2. So the distance from V to M is 1 divided by 2. Now, when we know the projection onto the orthogonal complement, the projection onto M is just the difference between V and the projection onto the orthogonal complement. So we can take V and subtract this thing, and we will get 1 divided by 4 times 4 minus 1 is 3, 4 plus 1 is 5, 4 minus 1 is 3, and then 0 minus 1 is minus 1. So the projection of V onto M is 1 divided by 4 times the vectors 3, 5, 3 minus 1. And the distance from V to M orthogonal complement is the length of this vector, which is 1 divided by 4 times the square root of 9 plus 25 plus 9 plus 1, which is 44. So the outcome is that the distance from V to the orthogonal complement of M is root of 11 divided by 2. And this completes problem 4. Problem 5. Let N be the subspace of E4 generated by the vectors V1, which is 1, 1, 1, 0, V2, which is 1, 0, 1, 1, and V3, which is 2, 1, 2, 1. Determine an orthonormal basis in the orthogonal complement to N. Solution. Let us start by finding some basis in this orthogonal complement. And element X belongs to the orthogonal complement if and only if it is orthogonal to the vectors V1, V2, and V3. So the scalar product between X and V1 should be 0, the scalar product between X and V2 should be 0, and the scalar product between X and V3 should be 0. The scalar product between X and V1 is X1 plus X2 plus X3, so this should be 0. The scalar product with V2 is X1 plus X3 plus X4, this should be 0. The scalar product with V3 is 2x1 plus x2 plus 2x3 plus x4. This should be 0. So we get a homogeneous system of linear equations with matrix 1, 1, 1, 0, 1, 0, 1, 1, 2, 1, 2, 1. Let us reduce this matrix to a row echelon form using Gauss elimination. So we use this 1 to kill everything else in its column. So we subtract row 1 from row 2, and we subtract twice row 1 from row 3. Row 1 remains the same. Row 2 becomes 1 minus 1 is 0. 0 minus 1 is minus 1. 1 minus 1 is 0. 1 minus 0 is 1. And row 3 becomes 2 minus 2 is 0. 1 minus 2 is minus 1. 2 minus 2 is 0. 1 minus 0 is 1. We see that row 2 and row 3 coincide, so we can delete row 2, and we get the matrix 1, 1, 1, 0, 0 minus 1, 0, 1. This is already kind of row echelon form because we have the first column and the last column together give us the identity matrix. So we can take x2 and x3 as free variables, and then from the first equation we have x1 is equal to minus x2 minus x3. x2 is a free variable, so it's equal to x2. x3 is equal to x3, and from the second equation x4 is equal to x2. In the vector form, x1, x2, x3, x4 is equal to x2 times minus 1, 1, 0, 1 plus x3 times minus 1, 0, 1, 0. So the vectors w1, which is minus 1, 1, 0, 1, and w2, which is minus 1, 0, 1, 0, form a basis in the orthogonal complement. So let's now do Gram-Schmidt. First, we normalize the first vector, w1. So u1 is w1 divided by its length. So it's a vector minus 1, 1, 0, 1 times 1 divided by the square root of 1 plus 1 plus 0 plus 1, which is 3. So the first basis vector is 1 divided by the square root of 3, minus 1, 1, 0, 1. On the next step, we compute the auxiliary vector u2 tilde, which is the second vector w2, minus u1 with the coefficient, the inner product between w2 and u1. Since u1 is w1 divided by the length, we can rewrite it as w2 minus w1 with the coefficient, the scalar product between w2 and w1 divided by the scalar product between w1 and w1. So the computation, so u2 tilde is w2 is minus 1, 0, 1, 0, w1 is minus 1, 1, 0, 1. The square of the length of w1 is 3, and the scalar product is 1 plus 0 plus 0 plus 0 is 1. So it's the first vector minus 1 divided by 3, the second vector. So we will get 1 divided by 3 as a coefficient. Minus 3 plus 1 is minus 2. 0 minus 1 is minus 1. 3 minus 0 is 3. And 0 minus 1 is minus 1. So we take as u2 2 tildes the vector without the coefficient minus 2 minus 1, 3 minus 1. And we normalize it. So the second basis vector is the vector u2 2 tildes divided by its length, which is minus 2 minus 1, 3 minus 1, times 1 divided by the square root of 4 plus 1 plus 9 plus 1, which is the square root of 15. And now we have the answer that the vectors u1, which is 1 divided by the square root of 3, minus 1, 1, 0, 1, and u2, which is 1 divided by the square root of 15, minus 2 minus 1, 3 minus 1, form an orthonormal basis in the orthogonal complement to n. This completes problem 5. Some additional problems and questions. Question 1. Give an explicit formula for an inner product on R2 for which 1, 1 and 2 minus 1 is an orthonormal basis. Question 2. In the Euclidean space Rx2, with the inner product given by the product between f and g is the integral from 0 to 2 f times g dx, find an orthonormal basis in the orthogonal complement of the space n consisting of all polynomials, which has value 0 at the point 1. Question 3. In the same Euclidean space, find the distance from x to the space of all polynomials which have value 0 at the point 1. Question 4. In the same Euclidean space, find the orthogonal projection of x squared onto the same space of all polynomials which have value 0 at 1. And finally, question 5. Find an orthonormal basis in the orthogonal complement to the subspace of E4 spanned by the vector 1, 1, 0, -1. Thank you very much and see you next time.